Thank you for the introduction. Hello, everyone. So today I will talk about pseudo-randomness sequence and for automatic and morphic sequence along some specific subsequences. So at first I will make a quick reminder on automatics and morphic sequences. So I start with the Thue-Morse sequence or the Thue-Morse sequence. This is the automaton for the Thue-Morse sequence, and the input is a binary word. In this example, it is 13, which is 1101, and we read left to right the digits, and at the end we read the value in the states. So there is 1, then 0, then 1. So the 13 value for the Thue-Morse sequence is 1. And in general, for the automatic sequence, you can find an automaton. You have an equivalent definition by the morphism. The Thue-Morse sequence is generated by the morphism F with 0 goes to 0, 1, and 1 goes to 1, 0. And we said that this morphism is uniform because all the images have the same length, here too. Then it is a 2 automatic sequence. And how can you get back the sequence? You apply recursively the morphism, starting by 0. So f of 0 is 0, 1. f2 of 0 is 0, 1, 1, 0, because it is a morphism. Then you do it infinite number of times, and you get back the Thue-Morse sequence. And to get the nth value, you look at the nth place of this infinite word. So this is the Thue-Morse sequence, the most famous automatic sequence. And in general, an automatic sequence is generated by an automaton or by a projection of a fixed point of a uniform morphism. A second example is the Golay-Rudin-Shapiro sequence with a more sophisticated automaton. And we do the same thing. In input, we have a 13, and we follow the arrows. So 1, 1, 0, and 1. Then the 13 value for the Golay-Rudin-Shapiro sequence is 1. And you can also find a morphism. So the morphism is A goes to AB, B goes to AC, C goes to DB, and D goes to DC. And you project the AB on 0 and the CD on 1. If you apply recursively the morphism, you get the word A, B, A, C, A, B, etc. And then you project on the binary alphabet. So you can generalize this construction by taking any word in base 2. So let's take W, a word in base 2, and EW of n, it's the number of occurrence of W in the binary expansion of n when you take a contiguous factor. And you have a general result that if you take this EW of n mod 2, this is a 2 automatic sequence. And it is easy to check if you take the particular word W of k, which is k1. If you take k equals 1, you get back the Thue-Morse sequence. So the Thue-Morse sequence counts the number of 1 in the binary expansion of n mod 2, modulo 2. And if you take k equals 2, you have the Golay-Rudin-Shapiro sequence. So this sequence counts the number of block 1, 1 in the binary expansion of n. And in general, for this particular word, we say that these sequences are called pattern sequences. So you can generalize automatic sequence by morphic sequence. You don't ask the morphism to be uniform anymore. The first example that I give is the Fibonacci word, when the morphism is 0 goes to 0, 1, and 1 goes to 0. And if you apply an infinite number of times this morphism to get the fixed point, you have 0, 1, 0, 0, 1, etc. And the length of the homomorphism applied n times is the nth Fibonacci numbers. Actually, you can find this, you can prove that this sequence is not automatic because the frequencies of its letters exist and they are not rational because they are linked to the golden ratio. And the second example of morphic sequence is the characteristic sequence of squares, which is a morphic sequence for this morphism. A goes to ABCC, B goes to BCC, and C goes to C. And you project the A, B on 1 and C on 0. And Ricci in 1963 proved that this sequence is not automatic because the gaps between the gaps, so the gaps are too large. And in general, this is not trivial to determine if a morphic sequence is automatic or not. And one example that I give is that the morphism of 0 goes to 1, 2, 1 goes to 1, 0, 2, and 2 goes to 0. If you get the fixed point of this morphism, you can prove that Bestel proved in 1978 that this is an automatic sequence for the morphism J. 0 goes to 1, 2, 1 to 1, 3, 2 to 2, 0, and 3 to 2, 1. And then you reduce the values mod 3 and you get the exact same sequence. Now I will talk about complexities. So how you can determine if a sequence is random or not. The first complexity that I introduced is the subword complexity. So if you take an infinite word on an alphabet sigma A0, A1, A2, etc., you said that the final word U is a subword of W if you have if there exists a I such that AI equals B0, A1 plus AI plus 1 equals B1, etc. This is a contiguous factor. And the subword complexity for a sequence or for an infinite word, it's you fixed k and you count the number of possible subword of the sequence. And the larger you have the subword complexity, the more different factors you have. So I give some properties for this subword complexity. You have trivially that the subword complexity at PS of k is bounded by the number of letters of your alphabet to the power k. If you take the periodic sequence 0, 1, 0, 1, 0, 1, you have only two different factors of length k, the one starting by 1 and the one starting by 0, sorry. You can prove that if there exists a case such that the subword complexity is smaller than k, then you have a periodic sequence. And the interesting case is when the subword complexity is exactly k plus 1 for all k. And in this case, you said that the sequence is a Sturmian sequence. And for example, you have the Fibonacci word that I gave sooner. So how you can use this complexity to determine if your sequence is random. You say that we said that the sequence is normal if every subword of length k appears in my sequence and with the same frequency. And in fact, almost every sequence are normal. This is a result from of Borel in 1909. But this is very difficult to construct normal sequence. But if you take randomly a sequence, it should be normal. One example of the first construction of normal sequence is the Champenown sequence in 1933. And how you construct this sequence, you add every binary numbers in the sequence. So you start by 0, then 1, then 2, which is 1, 0, then 3, which is 1, 1, then 4, 1, 0, 0, etc. And you can prove that this is a normal sequence. In fact, this works for every basis, but this is on the binary alphabet. And nowadays, we still don't know if pi is a normal number. So it's like square root of 2 or other famous constants. So the complexity that I study is linked to the feedback shift register. So what is a feedback shift register? It is a map between the binary field, the field of two elements, 2 power n into himself, and you shift all the first value, and the last one is a polynomial of the first one. And thanks to this map, you can construct an infinite sequence. So you give the first n terms, and the remaining terms are calculated with the relationship recurrence, which is Si plus n is the polynomial value of the n value before. And we call this sequence the output of the feedback shift register. And if your feedback shift register is too small, then you can consider that it is weak for cryptographic application because it will be too predictable. So if you want a robust sequence, you should have a large, you should be not generated by a too short FSR. And this is why we introduced the maximum order complexity, which is precisely the length of the shortest feedback shift register that generates the first n elements of my sequence. And we can use this complexity to an indicator of unpredictability of my sequence. And if this complexity is too small, and I know this is not good for cryptographic applications. So I give an example on how you can calculate this complexity. So for example, if you take the sequence 0, 1, 0, 1, 1, then the maximum order complexity of the two first letters is 1 because the two first letters are not identical. If you want to maximum at rank 3, the maximum order complexity is 1, you have to find a polynomial such that the third value is the polynomial of the second one, and the first one is a polynomial of the second one is the polynomial of the first one, which is 0 equals f of 1 and 1 equals f of 0. And then you can take the polynomial minus x plus 1. If you want that at rank 4 of the maximum of the complexity is 1, you do the same thing and you have the same system. So you can take the same polynomial. At rank 5, you do the same system and you have two different values for f of 1. So you have to increase the number of variables. If you want that at rank 5, the maximum order complexity is 2, you have the S4 is a polynomial of S3 and S2, etc. And this gives again a contradiction because you have f of 1, 0 have two different values. So finally, you can increase again the number of variables of my polynomial, and you can find a polynomial which is x plus y, which means that if you want a feedback shift register for the 5 first value, you need at least a length 3. Okay. You have a correspondence for the maximum order complexity and the spatial factor. So if you take a finite word U, you said that it is a spatial factor of another word W if there exist two different letters, alpha and beta, such that U alpha and U beta are also subwords of W. This is a right spatial factor because I don't study a two-sided infinite sequence. And you have a theorem from Jensen in 1989, which says that if you take a sequence on sigma and k the length of the largest spatial factor of the n first value of the sequence, of the word of the n first value of the sequence, then the maximum order complexity at rank n is exactly k plus 1. And if we take the same example than before, 0, 1, 0, 1, 1, you can immediately see that 0, 1 is the largest spatial factor of W because you have 0, 1, 0 and 0, 1, 1 in my world. Therefore, the maximum order complexity at rank 5 is 2 plus 1, which is 3. And we have the same thing than before. In fact, we use this theorem to make some estimates on the maximum order complexity for some sequence that we will see at the end of the talk. And the last complexity that I introduced is the expansion complexity, which is related to the generating series of my sequence. So this is ES, the expansion complexity at rank n is the least total degree of an algebraic relation for the first n terms of my generating series of my sequence. And you have a famous theorem from Crystal in 1979 that says that my sequence is P automatic if and only if its regenerating series is algebraic over Fp, which is equivalent that the expansion complexity is bounded. So you can ask if there exists a relationship between the expansion complexity and the maximum order complexity, and we will see later that you can't have such a relation. So you need both the complexities to determine the pseudo-randomness of a sequence. So this is the next point. What is a pseudo-random sequence? So we said that a pseudo-random sequence is a sequence that looks random but can be easily generated. And we do know the expected order for the former complexity. For the maximum order complexity, you expect something in log n. For the subword complexity, we said that almost every sequence is normal, then you expect 2 power n. And for the expansion complexity, you expect someone of square root of n. And then the question you can ask, if we already know the answer, but is the tumor sequence is random through this complexity? So the maximum order complexity is larger than n up to a constant. This is a result of Sun and Winterhoff in 2019. We already know that it is a classical result of the subword complexity of tumors is almost linear. First studied by Brelek and De Luca Variccio, and then this is a general result for automatic sequence. And you can find the algebraic relation of degree 5 for the tumor sequence. So none of this complexity are good for pseudo-random. And for pattern sequences, you have almost the same picture. And one question that arises, what happens to this sequence if you look only at square values? So I did not do the tumors along squares. So you take the 0, 1, 4, 9, 16 values, and maybe the sequence will be more random. In 2019, we have a result from Dromota, Modui, and Riva that says that this sequence is normal, which is the best possible for the subword complexity, regardless of this complexity. And it implies that this sequence is not automatic. So the expansion complexity goes to the infinity. We still don't know the growth of this expansion, but this is still better than bounded. And a result of Sun and Winter-Hoff in 2019 says that the maximum order complexity is looks smaller of the classical tumor sequence. In the maximum order complexity is larger than square root of n. So basically, we improve all the complexity for the tumors along squares than the classical sequence, and you can say that this is a better candidate for a pseudo-random sequence. And again, you have the same phenomenon for pattern sequence. And if you want to be convinced of the randomness and the non-randomness of the tumor sequence, here you have the 32 times 32 first terms of the tumor sequence, and you see a nice structure. And a random sequence should not have this kind of structure. And if you take the sequence along squares, you completely erase this structure, and it looks like more random. So now we want to generalize this result to polynomial subsequence. So if you take a polynomial of degree d, of degree larger than 2, and you look at the tumor sequence along this polynomial, we already knew that this subword complexity is exponential, which implies that the sequence is not automatic, and the expansion complexity goes to the infinity. And my result in 2020 says that if you take a polynomial of degree d monic and you look at the subword complexity of the tumor sequence or for pattern sequence, then the maximum order complexity is larger to n power 1 over d, which is a direct generalization of the result of Sun and Winter-Hoff. And how we prove this? We build a special factor of length n power 1 over d in the first n values. And to do this, we use the properties of the sum of digits function, because we have already saw that the tumor sequence is the sum of digits function in base 2 mod 2. And if you take two numbers a, b, and b smaller than 2 power r, then the sum of digits of a times 2 power r plus b, it's the same digit of the sum of digits of a plus the sum of digits of b, because the digits of a and b do not interact from each other. And we said that the sum is non-interfering. And we can use this to say that for every L and every n smaller than 2 power L, the sum of digits of n plus 2 power L is equals to sum of digits of n plus 2 power L plus 1. But if you take the specific value n equals 2 power L, then you have two different values, because you have the sum of digits of 2 power L plus 2 power L, which is 1, and the sum of digits of 2 power L plus 2 power L plus 1, which is 0 mod 2. Then in the first 2 power L values, you have built a special factor of length 2 power L. And we use this property to prove for every polynomial the same thing. So if you take a polynomial and for every integer smaller to 2 power L up to multiplicative constant, then the tumor's value along this polynomial sequence of n plus 2 power dl is equals to the tumor's value of the polynomial sequence of n plus 2 power dl plus r for any LR. This is exactly the same proof, but the hardest part is to find the spatial factor, not two occurrence of the factor. And so you look for a specific n close to 2 power L, such that you have two different values. And to do this, you need to control very precisely the carry propagation. And in base 2, you can do this. So is there any question? So sorry, this is so hard here. Okay. So you can generalize this result to the Zeckendorf base. So what is the Zeckendorf base? This is the numeration system based on the Fibonacci sequence. So 0, 1, 1, 2, 3, etc. And you can decompose every integer on the sum of Fibonacci numbers. And if you want the unicity, you ask for for non-adjacent terms, which is not two consecutive 1 digits on this representation. And I wrote up the first value for the Zeckendorf base, and you can see that you never have two 1 digits, a block of 1 1 in this base. And you can do the same thing as before. You take the sum of digits function, which is the analogous on the Zeckendorf base of the tumor sequence. So this is just the sum of digits. And if you look to this sequence mod 2, you can prove this is a morphic sequence. This is a result from Briere with a morphism A goes to AB, B, C, C goes to CD, and D goes to A. And you project the value A and D on 0 and B and C on 1. And so the infinite sequence is 0, 1, 1, 0, etc. And Dromota, Milner, and Spiegelhofer prove in 2018 it is not an automatic sequence because every Kerr-Connell are infinite. And this Zeckendorf base works very differently from the binary base because we have already seen that the carry propagation needs to be understood precisely. And here you have the transversality of the carry propagation. So if you have two 1 digits, one in order in diagonal, you have a carry propagations. And if you have the 2 1 in the same column, you have a right carry propagation. And especially the second case could never appear in the binary system, but in the Zeckendorf system it could appear. And if you ask for the determinism of the sum of digits function of the Zeckendorf base, if you look for the 33 times the 53 times the 53 first terms of this sequence, you do not see the structure. But if you choose a good number, which is 55, a number of Fibonacci, you can see clearly that you have a structure and it should be not random. And in fact, you can prove that the subword complexity of such a function is at most bounded by a quadratic function. And so we look for the maximum order complexity of this function, of this sequence. So let phi be the golden ratio. And with Damien Jamet and Thomas Stoll in 2021, we proved that the maximum order complexity of this sequence is larger than 1 over phi plus phi cube n plus 1. And in 2022, Shalit proved with Walnut that the ratio on the maximum order complexity divided by n have a limit of the bound of the constant that we have found, 1 over 5 plus 5 phi cube, and the lim sup is 1 over plus 5 square. And you can prove this with a walnut because the special factor property can be traduced in walnut. And so we can do this for polynomial subsequence. So we have another result. And maybe this sequence along square is more random. And if you look for the 55 times 55 first terms of this sequence, you do not see the clear pattern, such as before. And again, with Jamet and Stoll, we prove that if you take a polynomial of degree d and you look for the sequence along polynomial value, then the maximum order complexity is larger to n power 1 over 2d, not d but 2d, because you have the right carry propagation. And the Zeckendorf base was more difficult to handle because if you look for the squares of n plus 2 power l, then you have a very nice expression in base 2, thanks to the double product. But if you look to n plus Fibonacci number L or squares, it is not clear the expression in the Zeckendorf base now, because in general, a power of Fibonacci number is not a Fibonacci number. The only exception are 1, 8, and 144. So we use Lucas numbers, which are very close to the Fibonacci numbers. This is the same relation of recurrence, but you start with 2 and 1, and you have the property that the power of Lucas number is much simpler in Zeckendorf base. So we use this sequence to prove this result, and you can see directly the right carry propagation in the result. And we ask for estimates to see if maybe this result is not close from the truth. And for this, we use the result of Jensen, and we can define a graph, which is the direct acyclic word graph, the DAWG. How does it work? You take your word of length n, and for every subword y of w, you define the set of the ending positions of y, and you said that two subwords are suffix equivalents if all their ending positions are equals. And you build the graph, which is in fact the smallest graph that recognizes every subword of your word. So the edges are subwords and the vertices are letters, and two subwords are in the same edge if they are suffix equivalents. And we will see with the same example than before how you can find the special factor. So the example is 0, 1, 0, 1, 1. You have all here the list of its subwords. So you start with the empty word, and you have two different edges with 0 and 1, and you can add a 1 to 0 because 0, 1 is a subword of W. Then you can add a 0 on 0, 1 and a 0 on 1, and 1, 0 and 0, 1, 0 have all the same ending position, so they are in the same edges, in the same edge. And you can do this for all the subworld for all the world. 1, 0 can only be followed by a 1, such as 0, 1, 1. And finally, 0, 1 can be followed by a 1, and 1 can be followed by 1. And after you have this graph, you can look for the deepest node with two outgoing arrows. And here you have 0, 1. And This is the deepest node with 2 outgoing arrows, which means that the 0, 1 is a special factor, and it is the largest one. So this is exactly the maximum order complexity of my sequence, of my world. And we use this to look for the maximum order complexity of the Turing sequence along squares. And for the, I think this is 10 power 10 first terms, we have that the maximum order complexity looks like the square root of n. Along cubes, you have n to the power 1/3. And for the Zeckendorf base along squares, you have more like n to power 1/4, and which means that our result seems to be close to the truth. And after this, for cubes, you have to do more calculations, and you need a very strong computer to do it, and we couldn't have it. But we make some conjectures that we conjecture with the estimates that the tumor sequence along polynomial values, we have the right order for the maximum order complexity, which is n to power 1/d. And for the Zeckendorf sequence along polynomials, we conjecture that is n power 1/2d. And an open problem is you can look for other subsequence, not only polynomial subsequence. And here are the 64 times 64 first terms of the tumor sequence along primes. So there is no structure, and so the other problem is to prove a bound for the maximum order complexity of this sequence. And we have made some estimates. It appears like log of n, but we still don't know, because you have to be very precise for the binary digits of primes, and this is very difficult in general. So thank you for your attention.
Thank you, Pierre. Does anyone have any questions? Yeah, Hajime.
I have a thank you. I have a question about the last open question around those primes. So
yes,
today's theme is maximal. Maximal order complexity. But I have a question about the linear order. I forgot the name, but linear order complexity.
yes.
Is there a bound for linear order complexity of this one?
I don't think so.
No. Okay.
I think it still don't know.
Okay, but this is interesting. Thank you.
Yeah. Thank you.
Are there any other questions? So I guess it's probably too hard to prove something in general for all automatic sequences.
You can find some trivial example that this construction doesn't work. For example, if you take the characteristic sequence of squares along squares or along cubes, this doesn't work. But if you take the sum of digits function for numeration systems, you can do the same thing. But I don't think a general result can exist.
Okay. All right. If there are no other questions, thank you again, Pierre.
Thank you.
And thank you to all the participants. We have one more seminar in 2 weeks on, I think, July 11th. And that will be the last seminar before we take a break for the summer. And we'll start again in September. All right, so thank you all very much. And I'll see you all in 2 weeks, hopefully.
Thank you. Bye.
Thanks. Bye, everyone.